Welcome back, everybody. So this is the video for exercise 2B on page 115 of the workbook. And I'm hoping that if you're watching this video, you've at least made an attempt at this problem first and are checking your solution here. Okay, so the instructions for this problem were to use the fundamental theorem of line integrals, okay, to find the line integral of this vector field that we're given, okay, along a parabolic path, x equals y squared, that starts at 0, 0 and ends at 4, 2. Okay, well, we know from the fundamental theorem of line integrals that all that should really matter in this calculation are the starting and the ending points. The parabola is really not going to play a role in this question. Okay, let's maybe start by confirming that we really do have a conservative vector field. We need to know that in order to be able to use the fundamental theorem of line integrals. Okay, and we can test that by using the curl test. Okay, and again, that involves taking some derivatives. So we're thinking of f1 and f2 as just being the components in our vector field. And we're going to check and see if the derivative of f2 with respect to x is equal to the derivative of f1 with respect to y. Okay, so starting with f2, 3xy squared plus 2y. We need to take that derivative with respect to x. And if we do that, derivative of x is 1, and we're going to be left with a 3y squared. And derivative of 2y, that's going to just go away. Okay, and down below, the derivative with respect to y of f1. This time, we're treating x as a constant, so the e to the x is going to disappear, and the derivative of y cubed is 3y squared. And notice, we get two things that are equal, and that confirms that f is conservative. Okay, so that just confirms that we really can use the fundamental theorem of line integrals on this problem. Okay, and the next thing that we need then to use that theorem is a potential function. All right, and again, what we want to get a potential function is we want a scalar function little f that happens to equal the vector field that we started with. Okay, and so to be equal to a gradient, that means that we need the partial derivatives, fx and fy, to equal the components of our vector field. So that's our starting point. We're going to start from the derivative with respect to x being equal to our first component, and the derivative with respect to y being equal to our second component. And to get back to our function, we are going to need to take some integrals here. So the function f we can obtain in the first line by just taking the integral of e to the x plus y cubed with respect to x. Okay, if we do that, we're going to integrate e to the x to get e to the x. Y cubed is like a big constant in this case, so we're just going to get an xy cubed there. And then this is an indefinite integral, so we should have a plus c on the end, and that plus c may very well contain values of y, since we're treating that as a constant. Okay, so there's our first representation of f. Okay, we can move down here and do the same calculation starting from the partial derivative with respect to y. So we need to integrate 3xy squared plus 2y with respect to y. Okay, and if we do that, let's see, the first term, x is being treated as a constant, and 3y squared is going to integrate to y cubed. And if we integrate 2y, we're just going to get y squared plus a constant, which may very well contain x's. Okay, and the idea again is these two things that I'm underlining should both be equal to f of xy. So they need to be equal for this to make sense. Okay, so the question is, what would p of y and q of x be? What would they need to be so that these are equal? Okay, well, p of y, we're asking, what do you see down below here that you don't see up above? And what I notice is there's a y squared. Okay, so we'll make p of y equal to y squared so that We've got those two terms matching. And then q of x, there's an e to the x up here that's not down below. So we can balance the two equations by making q of x equal to e to the x. And notice if we do those two things, then both lines will agree, and we wind up with a potential function that looks like e to the x plus xy cubed plus y squared. Okay, and once we have that potential function, we are ready to actually calculate the integral. So this line integral along the parabolic path, all we really need to know to do that integral is the starting and the ending point. Okay, there's 0, 0, and therefore 2. We're just going to substitute both of those into our potential function and subtract them. Okay, so let's see what we get here. So for the first calculation, we're taking 4 for x and 2 for y. So e to the 4 plus 4 times 2 cubed plus 2 squared. There's f of 4, 2. Okay, and then we're going to take 0 and 0 and plug those in for x and y. Okay, and you can see the second two terms are just going to go to 0. We plug x and y equals 0 in. All right, so what do we get here? Well, let's do the arithmetic. So e to the 4th, 2 cubed is 8 times 4 is 32, plus 2 squared is 4, and then we've got a minus e to the 0, that's a minus 1. Okay, just do the remaining arithmetic there, and we get e to the 4th plus 35, and that should be our answer. And notice again, we were able to do that integral without doing any parameterization of our curves.